Good afternoon, students. Welcome to Lab 11, Galactic Speeds and the Hubble Law. This is the 11th lab in the Physics 110 lab course, and today we will be dealing with the age of the universe. It's difficult to get a solid idea of the age of the universe, as we need a lot of complicated astrophysics, specifically general relativity, in order to get around how these different dynamics work with gravity and time and dilation and all of that stuff. But estimations can be made using the data that we already have and the simple algebra that we've been doing this semester. In order to make these estimations, we will be extrapolating backwards from the current state of our universe to get an idea of what the universe might have been like billions of years ago. And this will be, of course, an estimation, so it will be a little bit crude, but it still gives us a decent idea of how the universe might have expanded in its early days. In order to better understand this, let's take a look at how the universe might have been created. So, our current theory is, of course, the Big Bang theory of how the universe was created. Everything existed at a singular point and then expanded outwards rapidly, eventually forming gas clouds, which formed into stars, and then star clusters, and then galaxies, and now galaxy clusters are forming. However, what we need to look at specifically is the fact that this is all expanding, and it's expanding at specific rates. Now, if we can look at how galaxies are accelerating away from the central point where everything started, we can get a better idea of how long things have been expanding for. So that's what we're going to do. We're going to use a very crude method to get an idea of how long these galaxies would have been expanding for. This leads us to the Hubble Law. Our assumption that we're going to be making for our estimation, as estimations usually require an assumption that simplifies things, and our simplifying assumption is that the speeds of the galaxies that we're viewing have not changed, so there is no acceleration. This is, of course, not true to real life, but it gives us a nice upper bound for the time of the universe, since if they are accelerating, it will be in the positive direction, not the negative direction, so they would be going faster. So this would give us an upper bound for the speed of the galaxies, not a lower bound for the age of the universe. So we can gather that the relationship between the distances and times for these galaxies is linear because the speeds of the galaxies haven't changed. So we use this to define a linear equation, that being that the speed of a galaxy is equal to some constant times the distance. And this constant is defined as the Hubble constant, and we will be looking for this constant throughout the lab. So the first thing that we need to look at is finding the speed of regression of a galaxy. And the speed of regression is called the speed of regression because it's showing how quickly the speed is, or how quickly the galaxy is moving away from a specific point or towards a specific point. So a specific galaxy will be regressing away from the observer, and that will cause the spectra of the galaxy to appear a bit redshifted. As long as it is moving away from the observer. So if the observer is moving faster than the galaxy, then the galaxy will appear redshifted. If the galaxy is moving faster than the observer, the galaxy will be moving away from the observer, and it will also appear redshifted. This is, of course, due to the Doppler effect, which we've discussed in class, and by looking at the spectrum of the galaxy, specifically in this lab we'll be looking at the hydrogen spectrum, we can see how this redshift takes form, and that'll allow us to calculate the velocity. In order to do this, we use the Doppler effect equation, which gives that the speed of the galaxy is equal to the change in the wavelength divided by the expected wavelength multiplied by the speed of light. Of course, here we have it as the speed of the galaxy over the speed of light equals the change in wavelength over the expected wavelength, just because that reminds us that this equation is actually stemming from a unitless ratio. So the speed of the galaxy and the speed of light will be measured in the same units, as will the change in wavelength and expected wavelength. So this is actually stemming from a unitless ratio, although when we multiply in the speed of light, it will give us the proper units for the speed of the galaxy. And of course, the speed of light is approximated here as 3 times 10 to the 8th, as we do throughout this class. Now, once you have these velocities, you'll want to graph them versus your distance, and that will be allowing the linear equation to take effect. So we defined this linear equation here earlier, and we will assume that it holds for the data based on the fact that we know this equation has some function. So we assume that this equation holds, and we graph it. And so assuming that this equation holds, we can take that if we're graphing v versus d, then the h, Hubble constant, has to be the slope of this line here. So if you graph these and find this slope computationally or via your own calculations, you'll be able to say that the slope is your Hubble constant. And that's how you'll find the Hubble constant from the data that we'll be gathering in the data collection video. Now that you have the Hubble constant, we know that v equals h times d, and that vt equals d, where t is the age of the universe. We can find an equation by substituting this first equation into the second equation, and that will get us that t equals 1 over the Hubble constant. And so that's your age of the universe calculation. And you do have to make sure the units are right and that the units all agree, but this will be your proper equation once you get the units down. Now, of course, like I said before, this is an estimation since it assumes that the galaxies are not accelerating, which we know that in real life the galaxies are actually starting to accelerate as the distance from the central point of the universe increases. However, this allows us to get an upper bound for the age of the universe. Now, I will discuss the exact assignment in the data collection video, but I'll discuss it again here. The assignment for this week is to turn in your values for the velocity for each galaxy, along with your value for the Hubble constant, and a graph of your velocities versus distances, and finally your age of the universe. And that's all you need to turn in. You can either put it in a document for Excel, or you can take a picture of your graph and send it to me via email, or you can write it all down on paper, or really anything you want, as long as I can get the general idea of the data and all of those bits are included. All right, good luck.